Bismillahirrahmanirrahim. Assalamu alaikum. Lecture number 5, unit number 8. The title of unit number 8 is Functions and Graphs. The topic of this video lecture is we will discuss linear, quadratic and square root function, and at last we will discuss the inverse of a function. If a function is bijective, then the inverse is possible, and that inverse will be also a function. So how we can find that inverse, we will discuss that at the end of this video lecture. To begin, first I will explain the linear function. A function of the form which is written in the form f of x is equal to mx plus b, where the m and b are constants. These are constants. So a function which is written in this form, f of x is equal to mx plus b, such type of functions are called linear function. If you see to the right side of this function, this right side is algebraic expression in which the power of the variable, the highest power of the variable is 1. So you know from the previous classes that when in an expression that the power of the highest variable is 1, so that expression is a linear expression. So in this case this is written in the form of a function, so that's why this is a linear function. Okay, now you know that this is not the multiplication of f and x. This is a notation for the function, that this function f, the mapping f, is dependent on the variable x. X is your independent variable. So this x is an argument, independent variable. So this will be read as f of x, which is m multiplied by x plus b. Now so this is the form of a linear function. If I put let's say this is a linear function. Now let f m equal to 0, then this linear function will become f of x is equal to b. So this is a constant function. Whatever you plug in place of the argument x, you will always get b. So this is a constant function. Okay, now if m is equal to 1 and b is equal to 0, because m and b are the constants, so then the linear function will become f of x is equal to x, and such type of functions are called identity function. So the special name of such functions are identity function. Now considering examples, let's say if I take an example, f of x is equal to x plus 1. Here the value of m is 1 and the value of b is 1. So this is a linear function. If I consider another example, g of x is equal to minus 3x plus 4. This is also a linear function. Remember that the graph of the linear function will be always a straight line in two-dimensional plane. So this is an important point you must need to keep in mind. Note the graphs of linear functions will be always straight lines in two-dimensional plane. This is point number 1 to be noted. And point number 2 is the domain of linear functions is the set of real number. R is the domain. So the domain of the linear function is the set of real numbers denoted by capital. So this is the domain. Mean every real number will be defined on every every linear function must be defined on any real number. So if if a linear function is defined on any real number, so it means that the set of the domain contains all the values from the set of real numbers. So that's why domain is domain domain is equal to set of real numbers. Now switching towards the quadratic function. Quadratic function. Quadratic function. A function f is said to be quadratic function if it is written in the form f of x is equal to ax square plus bx plus c, where a is not equal to 0, because these a, b and c, these are the constants, but we will impose the condition that a is not equal to 0, because if a is equal to 0, so this a0 multiplied by this x square, you will get this term equal to 0, so you will get bx plus c. So that will become linear, that will be not remain the quadratic. So for the quadratic function, the form of the quadratic function will be always this is the standard or the general form of quadratic function. Okay, now if a is not equal to 0, so then this standard form or general form is said to be quadratic function. Now I'm considering an example. Let's say f of x, so this is 3x square plus 4x plus 1. So this is the example. Now in this case, you see that x is your independent variable, this is your argument. Independent variable is also called argument. So if you put any real number in any quadratic function, so you will get a defined value. So it means that for all real numbers the quadratic functions are defined. So if for all real numbers the quadratic functions are defined, so it means that the domain is the set of real numbers for the quadratic function as well. So in this case, domain of quadratic function is the set of real numbers denoted by capital R. You need to remember these, because in most of the exams examiner asks about the domain and range of the function. So remember, if a function is a linear function, so without checking, without putting the values from the set of real numbers and looking that the function is defined or not. If the function is linear, so remember that function will be always defined for any real number. So R is your domain. And similarly, for the case of the quadratic functions also, the domain is the set of real numbers. Remember, the graph of the quadratic functions is always in U shape. Graphs of quadratic functions is always in U shape. So this, you also remember this point. So this is the quadratic function. Now moving towards the square root function. Okay, square root function. Square root function. A function f of the form f of x is equal to square root x. This function is called square root function. Now in this case, x is your independent variable. Whenever you plug x as an independent variable, so to get the dependent variable, mean to operate a function on that x, you will take the square root of that value. So this is the definition of the square root function. Now remember, this study comes under the subject which is known as real analysis, and in real analysis we always look for the we always look for real. We didn't go towards the imaginary. So that's why if I discuss the domain of this function, so I will impose a condition that x must be greater than or equal to 0, because if I put minus value, negative value in place of x, so there must come iota. In case of the real, in case when we are studying calculus or real analysis, we always avoid iota, we always avoid complex numbers. So that's why f of x, the square root function, you will must impose this condition. It means that your domain is always a non-negative real number. So the domain of this function is mean square root function, all non-negative. 0 is included, because if you put 0 to square root of 0, you will get 0. So 0 is a defined value, so that's why this function is defined on the 0. So 0 is included. So all non-negative real numbers, so this is the domain. This is the domain of the square root function, and this is the definition of the square root function. Okay, now moving towards the inverse of a function, which is the, now we will discuss this inverse of a function. Now you people know that inverse of a function is possible only when a given function is a bijective function. For example, if we have, I am discussing inverse of a function. Now our target is to discuss the inverse of a function. So in this case, let's say if I have a function f from x to y, and this function is on to a as well as 1 1, mean this given function, if this given mapping f is onto a as well as 1 1. Okay, now you people know that when a rule or a relation is said to be a function, if there is a unique element, a unique value of each input a function gives, so that is said to be that relation is said to be a function. And if all the codomain is covered, mean for every codomain value there is some pre-image, so that is called the onto function. And when for every image, mean for every value of the codomain, you have a unique pre-image, so that is the function. Actually, if you see, if you want to check that the relation is a function or not, so for every domain value you must have a unique image in the codomain, so that relation is said to be a function. And when you are checking that the given function is 1 1 or not, so you will see that for each codomain value there is unique pre-image in the domain. So this is a little tricky point, you must remember that. So I'm considering that f is a function which is 1 1 as well as onto, so this function is said to be bijective. If this function is 1 1 and onto, then we can say that f from x to y is a bijective function. So whenever a function is bijective function, whenever a function is bijective, so then the inverse of that bijective function is a function, and that inverse is also a bijective. I am explaining this point with the help of the example. Let's say this is my set x, this is my set y, and the rule between set x and y is, let's say, f. Let's say here is 1 2 3, and in the codomain I am considering a b, and let's say map a with 1 under this function, 2 with b, and 3 also with b. So now this rule you see in this figure in this arrow diagram, this is a function because for every domain value you have unique image in the codomain. Per 1 unique image a under this function, per 2 you have unique image under this function f, and per 3 b is also unique under this image under this function. So this f from x to y is a function. This is a function. This is a function. Okay, now I am checking that the function is onto or not. So this is onto function because the codomain and range are equal. Set y is your codomain, and the values that you get by from the putting inputs in the function mean when you put 1 you will get a, when you put 2 you will get b, and when you put 3 you will get b. So you see that you get from the inputs, when you put that in the function you get a and b. So actually that is your range. So in this case range and codomain are equal. So when range and codomain are equal, the function is onto. In other words, we can say that your codomain is covered. Your codomain is covered. Your codomain is covered mean per every codomain value there must be some pre-image. Per a the pre-image is 1, per b the pre-image is 2 as well as 3. So all the codomain is covered. So this function is onto as well. So now this is onto. Now I am checking for the 1 1 function. Remember that a function is said to be 1 1 that for every image that is present in the codomain you have a unique pre-image in the domain. You have a unique pre-image in the domain. So here if you see, b is the image of 2 and 3. So for b the pre-images are 2, mean for b the pre-image is not unique. So that's why this function f is not 1 1 function. So if it is not a 1 1 function, so this implies that this function is not a bijective function. So if it is not a bijective function, so the inverse of this function is not possible. I say this point in the sense that when you find the inverse, mean you change domain into codomain and codomain into domain, so you will get a relation. That relation will be not a function. For example, you see that whenever I am finding the inverse, so I will just, this is the notation for the inverse, f power minus 1 mean the inverse of this function. This f power minus 1 is not equal to f divided by 1 divided by f. This is the notation for the inverse function. So you will shift the codomain in place of the domain, and domain in place of the codomain. You will just shift range into domain and domain into range. That's the simple way to find out the inverse. So that will be ab, and here will be 1 2 and 3. So now a is linked with 1 and b is linked with 2, a is with 3. So you see that this is your inputs, this is your domain. So according to the definition of the function, for each input you have unique output. So b is your input, and for this you must have a unique output, but here is not a unique output. You see that for b you have two outputs, 2 and 3. So that's why f inverse from y to x is not a function. This is not a function. This is not a function. This is not a function. So because this is not a bijective, so that's why this is just a relation. Whenever a function is bijective, so its inverse is also a function. For example, if I take an example, let's say x, let's say this is y, here is f, this is 1 2 and 3, let's say, and this is a, b and c. Map 1 with a, b with 2 and 3 with c. So you see that this is a function because for each input you have unique output. This is onto because the codomain is equal to range, and for each image a, b and c are the images of 1 2 and 3 under this function f respectively. So for each image you have unique pre-image. For a the pre-image is 1, unique. For b the pre-image is 2, unique. For c the pre-image is 3, unique. So that's why this function f from x to y is bijective. You see that this is bijective. So now if it is bijective, so we will take we will find its inverse, and the inverse will be a function, and that function will be also a bijective, now what will be its inverse? Its inverse will, you need to replace range by domain and domain by range. This is the range of the function f, and when you are finding the inverse of the function, so this range will become domain. I am just changing range into domain and domain into range. You see it here. So A is associated with 1, B is associated with 2, and C is associated with C. So you clearly see that f inverse, this is a function, you may represent it with G, W, X, you can. So from Y to X. So this is a function, and this function is also bijective. So you see that if the given function is bijective, so this from X to Y, mean X is your domain and Y is your range, codomain set. So when you have this is bijective, so its inverse will be in this form. This f power minus 1 is not equal to 1 divided by f. It is the inverse. You may represent it with G. So this is from Y to X, mean your range in the case of the inverse is domain and your domain is the range. So this is also bijective. So remember, when a function is bijective, so its inverse will be a function, and that inverse function will be also a bijective function. This is the point. Okay, so I am writing it in the compact form. You see, let's say f from X to Y is a bijective function. Now if it is a bijective function, so y will be equal to f of x for all x belongs to capital X. Mean when you take the value of the value from the set X and put and give to the function, so you will get a value that will be in the set Y. You may write it here. Okay, now this is a bijective, the inverse is possible, so that inverse is denoted by f of minus 1, and this range is changed into domain, and domain will be changed into range. You see that here X is your domain set, here it is your range set, Y is your domain range, here it is the domain. So now in this case, this will be also a function, and that function will be also a bijective function. Now here you see that this function will take from the set of Y, from this set, so f inverse of Y. This f inverse is nothing but this just represent the inverse function. You can represent it with G. So you see that this will take the values from the set Y and gives the value when this function operate on this argument Y. So you will get a value that must be in set X, because this is your range. So for all Y belongs to Y, you will get X belongs to X. So this is the inverse of a function. Okay, now remember that when you take twice the inverse, so you will get the original function, because you know that f and f inverse are the inverses of each other. So this is the okay. Now if I discuss the domain and range, now in this case, if you see if I consider this function, so you clearly see that domain of f is equal to range of f inverse, because this X is the range of inverse function and this is the domain, and range of f is equal to domain of f inverse. I am telling again and again that f inverse is nothing but this is an inverse function. Inverse function is itself a function. Okay, so this is all about the inverse of a function. How you can find out the inverse of a function? There is a method to find inverse of a function. First we will write a function in the form y is equal to f of x. In first step we need to solve the function in terms of x for y. Okay, so the method that how you can find out the inverse of a function will be discussed in the coming video lecture. Thank you.